Hello, my name is Daryl Holland, and I would like to welcome you to our course on how to run the vertical milling machine. I'll be your instructor as we explore the intricacies of running the Bridgeport vertical mill. We will be showing you how to set up your mill, basic milling operations, plus I will share with you over 20 years of tips and tricks that I have perfected in running a Bridgeport type machine. We'll show you a lot of cool accessories that are available for the machine and how to get maximum performance out of these accessories when properly used. For those of you that have joined us in our course on how to run a lathe, many of you will remember my machinist philosophy, listening to the machine. Yes, the machine will talk to us if we have the ears to listen, and we will show you what to listen for in this course. We're going to also cover how to purchase a new or used machine, what to look for, best buys in the field, etc. So without further ado, let's get started. We owe a lot to a gentleman by the name of Eli Whitney, who in approximately 1798 developed the first milling machine. Now I think Mr. Whitney, if we can go back and look, took a look at a lathe, and we look at a lathe, if we were to apply an arbor from the headstock to the tailstock and mount a cutter on that this could be used in a milling operation to remove material. Now if we were to take the same lathe, mount it in a vertical position, again with a cutter protruding from the headstock, moving our lathe bed in a horizontal position to move longitudinally as well as transversely, this would allow the concept of the first vertical milling machine. The vertical milling machine is by far the most popular of milling machines. However, the early horizontal models allowed rapid removal of a tremendous amount of stock. We will see horizontal milling machines that weigh several tons and would use cutters that were 4, 5, 6 inches in diameter. It's important to remember also that in approximately the same year, Mr. Whitney was granted production by the U.S. government for approximately 10,000 muskets. Now up until this time, remember, everything was produced by hand. We had skilled craftsmen, each responsible for producing that individual musket or part. Mr. Whitney's concept was to be able to use an assembly line of machines producing those parts that would interchange with one another. And I think that this set the stage for the Industrial Revolution and made America the great nation that it is today. With the advancement of our technology, we've also seen CNC machines, profilers, etc. And this has allowed us to do unlimited things in the machine industry. For those of you that would like more history on this, please consult your local history book on the machine trades, and I think you'll find it fascinating information. Let's take a few minutes and become acquainted with the basic vertical milling machine. This particular machine is a J-Series Bridgeport. I've had this machine for over 20 years. We've been very good friends. We've produced thousands of parts in that particular time. This is a step pulleyed system. You can see through the side window here the exposed step pulleys. This, in my opinion, is probably the most versatile. They also make a variable speed that on the front of the head we have a crank that will increase or decrease the RPMs. You'll find in working with one of those that is more of a pain in the tail versus the step pulley system. In a step pulley system, we'll be dealing basically with 8 RPM ranges from 80 to 2720 RPM. This will cover about 99% of all of the basic operations that you would be asked to do in a vertical mill. Vertical mills come in different sizes. This is a knee type machine where the knee raises and lowers, allowing us to place the workpiece closer to the headstock. This particular mill is a Bridgeport J-Series with a 9x42 table. The depth of the table is 9 inches. The length of the table is 42 inches. You can also get a 48-inch model. There's some varying models that are available: Wells Index, Lagund, Jet, Acer, all build quality Bridgeport style machines, some a little bit larger. Let's not overlook the importance of a small benchtop type vertical mill. Many of you who have a small shop work out of your garage or home will have these small benchtop machines. They're an excellent machine for small light-duty work, doing second and third operations, again on small parts. Due to their compact size, you cannot machine real heavy-duty parts or take heavy cuts with them. This is where a larger stable floor model machine comes into play. This particular Bridgeport is going to weigh 1,500–1,600 pounds when properly tooled. Let's take a few minutes to become more intimate with our Bridgeport milling machine. Remember, this is a J-Series Bridgeport with a step pulley system. This particular machine has a 1 horsepower motor. It is a 220 3-phase motor. They are available in 220 single phase, so if you're going to purchase a Bridgeport machine, keep in mind your electrical requirements. If you do get a new or used machine that has a 3-phase motor, you can go ahead and purchase a phase converter, and I'm going to go ahead and turn the phase converter on now, and we can listen. All right, our phase converter is activated. Our machine is now ready to go. The first and most important thing is, how do we turn the machine on and off? All right, usually located up around the motor, we have an on and off switch. All right, this one is located on the left side of the machine. We have a forward and we have a reverse. This particular machine is an automatic forward and reverse. Okay, we can switch back and forth if we're going to use it in a tapping mode or a drilling mode. Very important. Now let's take a look at the speeds on the particular machine. This has a step pulley system. We've taken off the windows along the sides, allowing you to see the different step pulleys on the inside. A standard step pulley machine has 8 different speeds that we can deal with. 4 back gear speeds, and those speeds are 80, 135, 210, and 325 RPM. If we're using a large diameter cutter, we're machining hard steel, or drilling and reaming that require slow speeds, we would simply put the machine in back gear. The high speed or direct drive speeds are 660, 1115, 1750, and 2720 RPM. So those are going to cover a broad range of drilling and reaming depending upon the diameter of cutter or drill that we are using. In order to change speeds on this particular mill, we simply loosen the lock gibs, pivot the motor forward, reach up on the sides, shift our V-belt to the right pulley system, push our motor tight, lock it down, we're ready to go. Now if we were to use back gear, there's a couple of levers that we need to change in order to shift the machine into back gear. They're located on the right side of the machine. This lever, you usually have a in and out stamped above it. Simply rotate it. Every now and then you can see that it's stuck right now, and that's because we've got gear teeth that are colliding. So in order to get those teeth to mesh properly, we're going to reach up and rotate the spindle on our right belt here. There we go. We simply reach up, rotate the spindle at the same time, and shift it over into the in position. We've got also another lever that's located on the top of the head. We're going to shift that as well. Now we're in back gear, and we'll watch closely and see the difference in RPM. Okay? Reverse. Okay, anytime that we switch to back gear, our forward automatically becomes reverse. Okay, because we're going through the transmission of gears to those slower speeds, we're going to change direction in order for the cutting edge of this particular drill to work. Now that we've stopped from back gear, another application comes into play. We want to turn the machine at a higher RPM. We simply rotate the top lever out, come over on the side and rotate this to the out position. Very important though that we keep in mind we have shifted gears, but the gears have not necessarily meshed at this point. So in order to do that, we can either rotate the spindle by hand or reach up on the top and take our wrench. And you heard that clunking sound. Is what's happened is it allowed the gear to drop down and mesh into our direct drive mode now. This is very important. We don't want to damage our machine by turning it on when those gears haven't meshed. If you do so, you're going to hear a terrific clunk, and it'll sound like we were tearing the transmission out of the headstock of the machine. So get in the habit of doing that. Now we're in direct drive. We turn the machine on and we're turning at 1115 RPM right now. You'll also notice at the top of the machine that we've got a handbrake, and watch closely the proper application of the handbrake. Machine's on, shut off our switch, just reach up and give it a little slap with the hand. We don't want to physically hold the brake on. Just reach up and give it, and it allows it to return to a neutral position. This slows the spindle down instantly, allowing us a more rapid change of tools in a production mode. We don't want to sit there and drink a cup of coffee while we're waiting for the spindle to slow down. We'll go over the final details of securing the collet in the chuck. You're going to have a little nubbin in the chuck that tracks off of the R8 collet. It's a little guide that's in the spindle that matches this slot to keep our R8 collet from spinning in the spindle as we tighten it up. So we'll simply insert it, rotate it around until it lines up, push it in place. We're going to reach to the top of the mill head and we're going to finger tighten the drawbar to suck the collet into place. Once we feel the draw nut come up tight, we're going to insert our end mill, choke it up nice and tight, reach up with our wrench, and we've noticed the brake on the top of the mill. Okay, we're going to put the brake on as we tighten the drawbar. Get it pretty snug. We don't want to twist it off. We don't want to damage the collet. We've showed you how to install the cutter. Now, here's a couple of tips and tricks on how to remove the cutter. We're going to reach to the top of the mill and apply the foot or hand brake. Put our wrench on top of the drawbar. With the brake on, we're going to go ahead and break the cutter loose. Once we see the wrench is starting to turn freely, we can loosen our grip on the handbrake. We're going to reach down and with our index finger and thumb, grab the cutter as we continue to loosen the drawbar. Once the drawbar is loose, I like to take the wrench, or you can take a plastic hammer and simply tap the top of the drawbar, and that breaks loose the collet from the cutter, separating the two for removal. Take your right hand, take your middle finger, put it on the collet with the left hand at the top, and we're simply going to spin the drawbar off, releasing the collet from the spindle. All right, now let's look at some more specifics in and around the head of the milling machine. This is our quill. Okay, you can see it's much larger in diameter than what many of you may be familiar with on a drill press. This gives us the necessary rigidity to machine or drill on close tolerance parts. We have the quill handle, we have the quill lock. If we want to lock it in position, we simply set our lock, and now the quill will not retract. Loosen it. We also have a quill stop. You can see we have two split nuts in this position. We'll simply adjust those, bottom them out, bring up our lock nut, and lock it in place. And this establishes a depth at which we can drill or mill to. Let's say that we've got a variety of parts and we need to drill a hole to a specific depth. Once we've established that depth, we'll simply reach up and lock these in place, and hole after hole is going to be drilled to precisely the same depth. So in a production application, having the quill stop is very important. Now you'll also see a lot of numbers when we zoom in and give you a close-up on the quill stop. These are in thousandths graduations. We'll start at 0 here, and let's say that we have our quill in the locked position. We'll use the side of the vernier scale, or you can scribe a little line on our top lock ring as a reference. For each rotation of the dial, there is 40 thousandths or 50 thousandths, excuse me, in each revolution. If we want to deepen that hole an additional 20 thousandths, we simply advance the dial 20 thousandths, hold it in place while we screw our lock ring up, and our hole now will be an additional 20 thousandths in depth. Very important part of the machine and how to understand that. Next, we have on the side a direct power drive for the quill, and this becomes a very useful operation if we're drilling or reaming and we want a very measured, controlled rate of advancement of the quill into our workpiece. You'll notice on the sides of the machine, when we turn it on, we have this dial here, and you'll see that now it is turning in a clockwise rotation. If we were to engage our feed clutch at this time, That allows the quill to advance, and we can progressively drill a hole deeper in this mode. If we want to stop it, we simply disengage the feed clutch at that time. It's also important to know that our quill stop will also disengage that. Watch closely in this direction as we apply the clutch now. We can see our quill is moving down. We're drilling the hole deeper, deeper, deeper. When we bottom out against our quill stop, we automatically disengage. Okay? Now, let's say that we want to reverse that. We've drilled down in the hole, or we have a special reversing operation. We're simply going to reverse the direction. We're now turning in a counterclockwise position. So if we were to engage our feed clutch now, you can see that we are retracting the quill. Watch our gap here, as you can see it increasing by our direct drive in the quill. Very, very important in a boring, drilling, or reaming operation when we want a precise, controlled feed. Many of you may be thinking, is it possible to change directions on the power feed in the quill while it is running? No, it is not. Once we've engaged our feed clutch on the side, we cannot change direction. Okay, we simply must disengage the power feed at that point. Then we can go ahead and change directions by pushing or retracting out this lever on the side. Remember, when it is turning in a clockwise position, that allows our quill to power down. When we are turning in a counterclockwise position, you'll see the rotation here, we are retracting the quill at that point. Many of you may be thinking now, do we have the ability to change the feed rates? Yes, we do. If we look closely, we have a lever here on the side. We'll take a closer look and show you how to change the feed rates on the power on the quill. We're now looking at the left side of the machine, and we're going to view the feed rate selector. It's got 3 positions. You can see we've got 1.5 thousandths per revolution of advancement of the quill. This bottom section is 3 thousandths, the position that we're in now, and the top mode is 6 thousandths per revolution. So if we're drilling or boring, we need a faster feed rate. We simply pull our knob, rotate it up into the 6 thousandths position, engage our feed, and now we have a much more rapid feed rate. Disengage our clutch. We want to drill, ream, or bore for a final finish, and we need a very slow feed. We'll simply use our feed rate selector to the 1.5 thousandths per revolution. You can see very, very slow feed rate. Okay, while we're on this side of the machine, let's take a look at another important feature, and that is a proper lubrication for the machine. This particular machine is fitted with the Bajur one-shot lube system. They're usually located on the left side of the machine, down around the base. Simply reach down, pump your lube handle 2 or 3 times, hold it up for 10-15 seconds, and this will pressure lube the slide on the knee area as well as the ways on the bed. Very, very important to machine accurately and preserve our machine for many years that we properly lube the ways as well as the slide on the knee. To lubricate the head, you'll see that we've got a couple of oil traps located here on the sides. We're going to use a lightweight viscosity oil. Simply pull the lid off the top of the trap, dribble oil in until it just beads over the top. We want to do this daily on our machine, okay? If we're working on a high production job where we're running that machine 8, 10, 12 hours a day, do this 2 or 3 times a day. The same with the lubrication points on the knee or the table. Oil is cheap. The replacement or having our new ways scraped because we failed to lubricate them is very expensive. Now let's take another minute and go over some of the other fine points of the head of the mill. The mill is able to do a variety of tasks by tilting the hill or retracting the head fore and aft. If we look on top of the column, you can see that we've got 4 bolts, 2 on this side, 2 on the other side. By loosening these bolts allows us to rotate or shift the head left or right. If we've got a job that's really large on the bed and a portion of it is hanging over the side, it may be necessary for us to loosen those bolts, pivot the head around in order to work at that specific station. You'll see the bolts that we have here that are located horizontally. They allow us to use this lever and retract the head fore and aft. All right, again, if we've got a big job and it's sticking out over the side of the bed, we can't get at it closely, we can simply shift and move. This column works on a large dovetail, allowing the head to move in and out 6 or 8 additional inches from where it is normally located. It also may be important in order to shift the head left or right. We'll come to the face of the milling machine again, and we can see we've got 4 bolts located here. We're simply going to loosen those bolts, and this is our adjustment here. You'll notice closely that we've got a vernier scale on the side measured in degrees that allows us to adjust that head left or right in its arc in order to machine a specific job. And we would simply install our wrench here, crank the nut in left or right in order to shift the head in the proper plane that we want to. And lastly, the ability to shift the head in or out. Let's say that we wanted to cut a back angle of 45 degrees or so on a specific part. We can do that. And we're going to loosen the 3 bolts that you see here on the side of the machine. Okay, loosen these 2. We're going to draw this one up loose and then just come back and snug them up a little bit. We don't want them loose, we don't want them real tight. And then this is our adjustment level that we can go ahead and turn, and this will allow the head to tilt back and forth. We'll deal more with the adjustment of the head and what we call the tramming in of the head when we get ready to set up the mill for actual work. But before we get to that point, we've got a lot more areas on the mill to cover. And let's start with the table. As we said earlier, this is a 9 by 42 size table, 9 inches deep, 42 inches long. That is how our mill size is governed. We've got a hand wheel on the left and right that, if we rotate, moves the bed longitudinally to the axis of the spindle. Okay? Keep in mind that this is called the x-axis. We will be dealing with that on the x and y axes later on in this series. On the knee, or some people refer to it as the saddle, we've got another dial that allows us to move the bed transversely or in and out in relationship to the spindle. So if we're going to be machining parts, we have a hole pattern, we can simply make our precise adjustments in 2 directions, on the x-axis or on the y-axis in relationship to the spindle. Next, we have the knee, and this assembly that you see here is called the knee, and we're able to raise and lower that again by a large hand wheel that we crank. Crank it in a clockwise position, raises the knee. A counterclockwise position lowers the knee. You'll also see a lever mounted on the bottom. This is the gib lock. Once we've made an adjustment to the knee and we want to lock everything in place for that final machining operation, we simply lock the gib in place. The same thing applies to the table. You'll notice that we have a gib lock underneath our digital readout scale. We're going to use an Allen wrench here, and if we wanted to lock the table in position, we would simply tighten that gib up. Keep your gibs adjusted. When you're working back and forth, loosen them. We don't want to put any additional drag on the gibs while we're in the machining operation. Also, on the left side of the knee, there is another gib lock underneath here. Again, it's a little lever. Just push it down. We don't want to really scrounge it down or twist it off. Make sure that when we're ready to move the table again on the x-axis that we loosen that gib. If we're going to dial in a part, have everything set, and we're going to run 100, 200, 300 of those parts, we want to make sure and lock our gibs down, positioning the table and the knee in an exact location so we have excellent repeatability and accuracy of the parts that we're either drilling or machining. All right, now let's take a look at the dials. The dials are going to become a very important part of the machine. We've got a lock nut here, and in order to adjust the dial for a specific setting, we simply loosen the lock nut by turning it counterclockwise, rotating the dial, and lining it up in the 0 mode. Okay, so we're zeroed now. Remember, each revolution of the dial is 200 thousandths. In the y-axis or the x-axis, each revolution 200 thousandths. When we work on the knee, each revolution of the knee is 100 thousandths. Okay, so keep those figures in mind. They're always on the dial, they're easy to see, but in order for you to get your Master Machinist certificate, as you will, you need to know the amount of travel per revolution of the dials on the mill. Now, while we're here, and we'll deal with it more a little later on the video, let's take a few seconds and go over the proper way to rotate the dial, okay? Oftentimes you'll see newer beginning machinists that are not capable of making a smooth transition with the dial. They'll go 1, 2, 3 revolutions with the dial. This is fine if we need to count revolutions, but in order to perfect your technique, we're simply going to allow this pear-shaped knob to float around the palm of our hand, and watch how smoothly now that I rotate. It's one continuous motion as this ball rotates around in the palm of my hand, okay? So we make nice smooth rotations of the dial when we're traversing the bed on the X or Y axis, okay? Now I like to count off of the knob on the top. If I'm making specific revolutions and I've set my dial, I'll just simply count as it goes by. 1 revolution, 2 revolutions, 3 revolutions, make my stop, lock the gibs down, and I'm ready to go on to the next part of the machining operation. Now it's also important to keep in mind, we've showed you the different rotations of the dial for if we were drilling or reaming in a hole pattern. But remember, the milling machine also can cut grooves, slots, and channels, and it's necessary to have this same smooth technique or rotation of the dials in order to get a smooth finish. So if we had an end mill in the machine, we simply want to advance in a very smooth, uniform motion. We don't want to go chop, chop, chop each revolution of advancing the cutter. We're not going to get the desired finish that may be required on that specific job. Now let's take a minute and go over to the right side of the table, and we'll look at what is called the power feed unit. We've showed you how to manually move the table left and right or in and out. They've also supplied a unique little tool. This one's made by the folks at Servo. Bridgeport also makes one, but it is a much bulkier machine that's got a lot of levers and linkage that is running on it. So if you're going to look for a power feed on the x-axis or on the y-axis or the z-axis, which is raising or lowering the knee, check with the folks at Servo. They make fantastic products. This one operates on a rheostat. We have a little direction knob here. If we shift it over to the right, the table is going to travel to the right. If we shift it over to the left and start our rheostat, you can see the direction of the table as we travel. If we're making a long uninterrupted cut, this is really a handy way of getting a very smooth, uniform finish, okay? So we have the little rheostat, and those are usually numbered from 1 to 9, 9 being the fastest, or rotate it back down to 1, and you can see that we're on a very slow feed rate depending upon the type of machining operation that we are engaged in. This is a real benefit. If we want to traverse quickly, they have a power override on this particular button, and you can see that it takes us in a fast mode. If we need to move in a hurry to go across from one hole location to another, and we need to get there in a hurry, this is the button to use. Works really well. Now we go in reverse mode. Okay, when we stop and we shift, once we've maintained that alignment, we can shift left or right without a problem. If we have moved the dial by hand, we may not pick up the necessary gear drive. So simply rotate the handle back and forth until it meshes, and this way when we turn on, you heard it go clunk. That was allowing this servo feed to engage the worm gear and drive the lead screw, powering the bed left or right. Okay, that pretty well covers all of our features on the mills. We've showed you about the quill, how to change angles on the head, how to properly rotate the handles, the X and Y axes of the bed. Remember, the X axis moves the bed left and right. The Y axis moves the bed transversely or in and out in relationship to the spindle. The hand wheel, which powers the knee, moves it in the, you guessed it, Z axis, up and down, all right? Those of you that are a little slow on the uptake, we've got X-axis, Y-axis, raise and lower the bed is the Z-axis. All right, now let's get on to more important things, and we will deal with the vise. It's very important that we purchase a good quality vise for the milling machine, and I think for the money, a Kurt Angelock is probably one of the best vices that you can purchase, okay? We've spent a lot of money on the mill. It's important that we tool it properly with good quality fixtures, thereby assuring that we are going to get good quality finished parts in the machining operation. If we have a vise that's poorly made, if the accuracy of the vise is such that we clamp apart, it shifts it out of square, it tries to squeeze and blow it out of the top, we are not going to be able to produce the quality products that our vendors desire. So a Kurt Angelock, again, one of the top vices. This is a 5-inch. They come in a variety of sizes, 4, 5, 6, and 8-inch. For most of your machining operations, a 5 or a 6 is probably the most versatile size. Make sure and get the swivel base for it, and this allows the vise to pivot left or right if we need to machine an angled slot or face something off in a different direction. Okay, very important accessory. You'll also notice that we've machined and installed a riser block underneath this vise. This gives us a little more lift to the vise. If we have parts that we mount in the vise that hang over the side and we don't want them to interfere with the table, having this little riser block in place is very, very important. Another neat little accessory on the Kurt Angelock vise is to take a little piece of neoprene, okay, and make yourself a little bracket bar as you see here, and this protects the ways. Keeps your chips and debris from getting under there. I wish I could sell this idea to the folks at Kurt Angelock, but they probably wouldn't pay me any more than a cold beer for it. But it's something that you can do, and again, it's a nice finishing touch on your machine. We've also got way covers. Again, this is something that you can build in your spare time. They're simply a removable cover to protect the ways, keeping all the chips and debris out. You'll see a lot of machinists, if they have tools or cutters or collets that they're working with, rather than have a way protector, they're constantly banging and clattering their tools back and forth. Okay, this is a very easy way to damage the surface of the bed, causing us to have to go by and resurface the nicks, chips, and dinks in the top of our table. The table is ground very accurately, and we want to preserve that accuracy by protecting it. You can build these out of pieces of 1/4-inch masonite. They do a wonderful job of acting as a tool rest, but most importantly, they protect your ways. Okay, you can see this part of the machine here is my scale for the digital readout. We'll show you the advantages of a digital readout a little bit later on in the course. Another thing to keep in mind are way covers. This is an accordion type cover that you can buy from the folks at MSC or any of the major tool houses, and these protect the ways of the machine from all of the chips, solvents, and oils that we may be dealing with. They have one that works across the saddle, and they have one that works on the column or the knee of the mill as well. You're going to get a lot of chips in here. You'll see a neoprene saddle that they'll put in there from time to time, and they work reasonably well, but by far the best protectors for your machines are these accordion style way protectors. All right, that pretty well covers a lot of the main features on the machine. We'll get into more of the cool accessories a little bit later on, coax indicators, drill chucks, etc.